Hello everybody. Today we're going to be looking at section 2 of chapter 15. There's only the two sections, so we're actually almost done with this chapter. Now section 2 is about properties of matter. Section 1 was about the composition, what matter is made up of, and section 2 is about properties. Now there is a two-part main idea to this section, so let's write it down right here. The first part is a physical property. A physical property can be observed without changing the identity of the material. A physical property can be observed without changing the identity of the material. We're going to talk about that in a moment. The second part to this main idea, a chemical property can be observed when one or more new substances are formed. Okay? So let's look at chemical and physical properties of matter. And we're going to start with physical properties. So, a physical property. What is a physical property of a substance? Well, it's any characteristic of the material that you can observe without changing the identity of the substance. Some examples would be color, shape, size, density. Can't change that. Melting point, boiling point, and there are more, but these are a few of the most common examples. Okay, so these types of physical properties basically have to do with the appearance and the behavior of the material. The appearance is how it looks, color, size, shape, volume, the state it exists in, whether it's a solid, liquid, or gas. Behavior is how the material acts under certain conditions. For example, what happens when it gets to its melting point? What happens if it's introduced to a magnet? Is it pliable or not? Is it viscous? Is it able to conduct electric charge? So these are examples of behavioral properties, behavioral physical properties. And I've got a nice picture right here with some examples on it, like crushing a can. If you crush a soda can, you haven't changed it to a new thing. It's still a soda can, it just has a different shape. Melting an ice cube. It's frozen water, but when it reaches the melting point, the molecules of the water begin to slide with each other, against each other. They're still water molecules, they're just in a different state. They're in a liquid rather than a solid state. Same thing for boiling water. When water reaches the boiling point, it will begin to evaporate, but even the evaporated molecules are still H2O. They're still water molecules. So this is just a physical change. Mixing sand with water, okay? Breaking glass, it's still glass even though it has cracks in it. Dissolving sugar in water, you still have the water, you still have the sugar, they're just mixed together. Shredding paper, it's still paper even though the pieces are smaller. Chopping wood, same idea. Mixing green and red marbles, they're still the green and red marbles and you can separate them easily. Sublimation of dry ice. It's going straight from solid to gaseous form, but the solid molecules and the gaseous molecules are still the same thing. They're still dry ice, okay? Now, we can use physical properties to help us separate mixtures that we've talked about already. Here are the ways that we can use physical properties to help us separate mixture. We can separate them manually. For example, if you have a salad, all you have to do is pluck out the onions if you don't like the onions. Magnetism. If you have a magnet, you can separate iron filings or iron-based particles from non-iron-based particles, because we know magnets will attract iron and anything made of iron. Dissolving. Salt water is made by dissolving salt into water, and if you evaporate the water, you separate out. You can also separate some substances by dissolving. Filtration. Put sand or put a mixture through a sieve where you have different sized particles in the mixture, and you'll separate the smaller particles from the larger particles. Crystallization. Now, if you've ever made rock candy before, you know you use a thick syrup, a thick sugar syrup, and you put a string in it, and you let the water evaporate out, and the sugar crystallizes on the string, and you get sugar crystals, and that's rock candy. Okay, so there's a number of ways we can use physical properties to separate mixtures, and here they are right here, so make sure you're aware of those. Now, physical change. If an object undergoes a physical change, that means you're changing one of those physical properties, but that doesn't mean you're changing the identity of the material. Like we said, you can crush the can, so it's undergone a physical change, but that doesn't make it a new substance. It's still a can. You've just changed the physical property of shape. All right, some other examples. Let's say state, all right, the physical state. For example, when iron reaches the melting point, it will melt, but it's still iron. All of the atoms are still iron atoms. Separating them through melting doesn't make them not iron atoms anymore. So it's just a physical change. You're going from one state, the solid state, to another state, the liquid state. Iron, interestingly enough, can also change color, another physical property, with temperature. The hotter iron gets, as you know, iron is typically a black metal, and as it heats up, it can become red. And if you heat it up even more, it can eventually become white. So it can change the physical property of color as its temperature changes as well. So physical changes simply means changing one of these things here, and it's still the same substance. You've just changed something about this, the physical properties, okay? Now, let's look at an application of physical change. What's a useful way to use physical change? Well, a process called distillation is a useful application of using physical change to separate a mixture. For example, salt water. If you evaporate out the water, you will be left with water vapor and salt. And the water vapor can be condensed into drinking water. It's called distilled water because it's in its purest form when it's distilled. So look right here. Here's an example. You have a flask with seawater in it, and it's sitting on top of, there would be some kind of heating element here to heat it up. And as the water evaporates out, it leaves salt crystals behind. The evaporated water can't escape through the top because it's stoppered, so it has to come through this tube right here where it's cooled down. This is called the condensing tube. The water is cooled down, and when that happens, it condenses in the tube and becomes liquid water again and drips out into this flask here. So here's your pure water, and that's called distilled water. Now, I don't know if you're aware of this, some of you may, but you can actually purchase gallons of distilled water at the grocery store. A lot of ladies use distilled water in their irons to make steam in their irons when they're ironing clothes, because distilled water is pure and will not leave behind deposits on inside and on the surface of the iron. And that way it's a cleaner iron. All right, so this is a good simple way to simply take seawater and convert it into drinking water. You all think that might be an important thing that we be able to do? I kind of think so. Fresh water is becoming more and more scarce on this planet as we use it up. So being able to convert drinking water from seawater is very important. Now, so that's an application of using physical change to separate particles of a solution. Let's look at chemical properties now. Chemical properties. This is any characteristic of a material that you can observe that produces one or more new substances. For example, if a substance is flammable, if you use heat it up or burn it, you can produce a new substance. Oxidation. Sometimes they're the same thing, sometimes they're not. Oxidation is also another chemical property. There are others, but I want to focus on these for right now. Chemical change is what takes place when you use a chemical process to convert one substance into another. So here's an example of oxidation. Water will cause iron to rust. So rusting is when the iron combines with the oxygen in the water molecule to produce this reddish material called rust. And it's not iron anymore. It's not pure iron anymore. It's a compound. It's iron oxide. So iron rusting is a chemical change. The rust itself does not have the same properties as the pure iron. Burning wood is another form of oxidation. And there goes my clock. Hang on, guys. Okay. Burning wood is another chemical change. When you put a flame to the wood burns and becomes ash, but it also releases a lot of oxygen into the air. Okay? So you get two different things. You get the ash, which is the leftover carbon, and you get oxygen. Completely different from the original wood. Metabolism. When you eat, the acids in your stomach break down the food into its compound components. So you don't have the food anymore. It's completely different now. Cooking an egg, and in fact, cooking an egg, baking a cake, anytime you cook or bake something, you're chemically changing it to something new. Electroplating, substances that decay, those are going through chemical changes, like the rotting banana. Putting together two chemicals and you get another substance when you mix them, because you can see the chemical reaction taking place, like vinegar and baking soda. It foams up and releases oxygen, and you can see that chemically taking place, and it becomes a different solution than what it was individually. Fireworks, same idea as burning. The chemical components in the fireworks burn up and emit light and sound, which is kind of cool. A chemical battery. the chemicals react and produce an electric current. Okay, so you're changing the form of the chemicals inside when they combine. Now, how do you know when a chemical reaction is taking place? I'm pushing it up so y'all can see better. Well, there are some clues to look for. For example, the substance will get hot. And I don't mean necessarily by flames. Sometimes you can add two chemicals and you get what's called an exothermic reaction. The two will heat up and there's no flame to be seen anywhere. So substances will get hot sometimes. Another clue could be just the opposite. It could also get very cold. You could see bubbles formed in some chemical reactions. You could get light formation, like with the firecrackers, or even sound. So there are a number of clues that can indicate that a chemical rather than a physical change is taking place. An application of a chemical change. Now here's an interesting application. What you have here is a container, and it's a baking dish. They've lined it with aluminum foil, and they've poured some baking soda on top of the aluminum foil, and now they're dissolving the baking soda in hot water. Well, the interesting thing, when you make a solution of baking soda on aluminum, if you put your tarnished silver in that solution, the aluminum and the baking soda will react with the tarnished silver on the surface of your flatware, and it will actually change the tarnished silver. It will shine back up again because you're going through a chemical change, and that will clean your tarnished silver. So that's kind of cool. So right here I'm going to put aluminum plus baking soda equals cleaned silver. It cleans the tarnished silver. So here's the baking soda and water, or aluminum, and you do have to have water in there. Aluminum, okay, and here's your tarnished silver. There's somebody's put the tarnished silver down on top inside the solution, and it cleans it. Kind of cool, huh? All right, not much more, guys. Last thing I want to look at. Some people think that when you go through a chemical change, you won't have the same substance anymore. And that's true. That part is true. You get one or more new substances when one substance goes through a chemical change. But here's the catch. Whenever a chemical change takes place, it does not change the total mass of the original substance. Okay, here's what I mean. We're going to talk now about the law of conservation of mass. Basically, it says mass is neither gained nor lost during any chemical change. The total mass of the substances before chemical change, and we call those the reactants. The substances that we have before the chemical change are called the reactants. The total mass of these reactants must equal the total mass of the new substances formed. Those are called the products. So the takeaway here, law of conservation of mass says the total mass of the reactants equals the total mass of the products. In fact, here's a nice little excerpt from a PowerPoint. Notice some of the components of the conservation of mass. Atoms are never lost or gained in a chemical reaction. They are just rearranged. The total mass of the reactants will be equal to the total mass of the products. The starting materials in a reaction are called reactants, and the substances that are formed from the reaction are called products. So let's look right here for a minute. Here is an interesting equation. This is called a chemical equation. The arrow represents the chemical reaction taking place. What's to the left of the arrow are the reactants. So here are the reactants. This is what we're starting with. And at the end of the chemical reaction, what you have left are the products. Okay? Now, what do all these letters and numbers mean? Well, these are chemical symbols for compounds. All right, you recognize this one, H2O. This is water. 2 hydrogen atoms and 1 oxygen atom is a water molecule. And we have 18 water molecules here. CO2 is carbon dioxide. It's carbon and oxygen. 2 oxygen, 1 carbon. And we have 16 of these molecules. Right here is just plain elemental oxygen. It always comes in pairs. We have 25 of them. And this is called octane. Octane is 8 carbon atoms plus 18 hydrogen atoms in one molecule. And we have 2 of these molecules. So notice what this is saying. If you take 2 octane molecules and add it to 25 oxygen molecules, and usually that's through a heating process, then what you'll get for your products after the chemical reaction is 16 carbon dioxide molecules plus 18 water molecules. Kind of cool. Now, what does that have to do with conservation of mass? Well, look. If we have 2 octane molecules, that means we have 8 carbon atoms, and 2, since we have 2 molecules, 2 times 8 is 16 carbon atoms total on this side. Look how many we have on this side. 1 carbon, and we have 16 molecules. We have 16 atoms of carbon here too. 16 here, 16 here. Right here, 1 single molecule of octane has 18 hydrogen, but we have 2 molecules. So 2 times 18 is 36 hydrogens. We'll look over here. In the water molecule, we have 2 hydrogens, but we have 18 molecules. 2 times 18 is, oh, guess what? 36. So we have 36 hydrogen, 36 hydrogen. Same for the oxygen. We have 2 atoms in a molecule, and we have 25 molecules. That's 50 oxygen atoms. But look over here. 2 times 16 is 32 oxygens. 18 oxygens here, 32 and 18 is, guess what? 50. So we have the same number of atoms of each element on both sides. Mass has been conserved. Okay? They're rearranged differently now into new substances, but they are still the same amount of mass. The total here is equal to the total here. So mass has been conserved. Look at this example here. When hydrogen reacts with chlorine, the only product is hydrochloric acid. If 18 grams of hydrogen react completely with 633 grams of chlorine, how many grams of hydrochloric acid are formed? Well, look what we've got. We've got 18 grams of hydrogen, and we're going to add to that 633 grams of chlorine. Now, these are our reactants. And they're going to combine chemically to perform how many grams of hydrochloric acid? This is going to be our product. Well, according to the law of conservation of mass, we have to have the same number of grams here that we do here. So 18 grams plus 633 grams gives us a total of 651 grams. So we have to have 651 grams of hydrochloric acid in order for mass to be conserved. Now that's not so bad, is it? That's pretty cool. Okay, guys, that's the end of the notes. And you will have some things to do this week to look at this. And I'll see you later. Bye-bye.